Okay, we're going to take a look today at the next step in the process of breaking down the mountains. But before we get there, we're going to go back and review some of the things we looked at last week. If you could take out a piece of paper and write down some notes, there will be a place for you to submit those notes at the end of this. So today we're going to look a little bit back at what we did in this week. We're going to look at rate of weathering, surface area, climate, and mineral composition. So rates of weathering can be affected by climate. We looked at this diagram in the activity yesterday, and this can be shown to show how the climate of an area really strongly affects what type of weathering we have. Cold and humid is going to have the water available, and that you need that alternating cold and warm that you get at certain times of year at high latitudes and high altitudes, and you're going to end up with something like frost action, strong mechanical. Then hot and humid is going to favor chemical weathering. So we have, this just shows an image of someplace in a jungle, and we have the hot and humid favoring the chemical weathering there. Also, hot and humid is going to favor the physical weathering agent of root action or biological action. Basically, plants like it when it's hot and moist. So you get a lot more plant action. Plants break down the rocks physically through root wedging, and also chemically they produce a small weak acid that helps break down the rocks as well. This image is showing us the original statue, or it's called an obelisk. It's called Cleopatra's obelisk, that was built in Egypt, thousands of years ago, and then a remake of it that is found in New York State. They're made of similar materials, but because they're experiencing different climates, one has had a much faster rate of weathering, the one in New York versus the one in Egypt. High altitudes and latitudes favoring physical frost action. You need the availability of water and the alternating cold and warm. It can't just be cold because the water would never be liquid to actually get into the cracks. This was a big point of discussion this week, was this idea of particle size, that changing the size by cutting something open or crushing it, you are exposing parts of the sediment that were inside to the agent of weathering. So you're allowing that surface that was at one time buried on the inside, or atoms that were buried on the inside, to now be exposed, which is going to cause everything to happen much quicker. So by cutting something open, you decrease the particle size, which increases the surface area. And it's very important when you're looking at things like this that you realize that we're comparing a whole object and then that whole object as crushed pieces. We are not comparing a boulder to one single pebble. It would be a boulder to a pile of pebbles that have an equal volume to the boulder. This is showing us something similar where we're breaking something down, increasing the surface area. Also, you want to consider the shape. When something becomes more rounded, they will weather at a slower rate for two reasons. Something that is more rounded or spherical has less surface area, and also corners are vulnerable. Corners will get knocked off very quickly during the process of abrasion as those rocks are bouncing along the bottom of a creek bed, or being, wind blowing sand grains around in a wind abrasion situation, or in a glacier where they're grinding along the bottom of the ice. The corners, or very thin pieces, oddly shaped pieces that are sticking out, will get knocked off first. As that happens, we have a quick rate of weathering at first as all those pieces fall off, and then as it becomes more rounded, the rate of weathering will slow down. Mineral composition, we studied that where we looked at, I shook all those different materials in a container, the candy cane. What else did I have in there? A rock and some chalk. And we saw that all those materials weathered differently in an abrasional system. This would be in all types of weathering, that the types of minerals that are present, so what type of rock you have there. Is it a very resistant rock, or is it a rock that is less competent? That will affect how a rock breaks down or weathers. So you can have things that have strong chemical composition. There's harder rocks. They will make the sharp edges that we see on the right here, versus the weak chemical composition of what we see here on the left, making these rounded hillsides, versus the sharp, more resistant shapes that we have over here. We go back to this, and it's going to ask us a question here. What are the products of weathering? So as the rock breaks down into these smaller pieces, what do we call these smaller pieces? They are called sediments. And sediments can be all different sizes. We can start up, the largest pieces, just any chunk that breaks off the crust could be a really large piece that's bigger than your kitchen table, might be considered a boulder. And then all the way down you go: boulder, cobble, fist size, pebble, thumb size, sand, like you'd see at the beach, silt, and then clay. And then even smaller than that, if you break it down into its smallest piece, it could be an ion. So little particles that are dissolved into the water. These are sometimes called clasts or sediments. Clast. Okay, we did discuss that when you make a soil out of these sediments, there's two types of soils that could be created. Residual is when the mineral material that's forming the soil, coming up from the bottom, actually formed in the same place that we're finding the soil. So it's from the bedrock that is local to that area. That's what the soil is being made from. A transported soil would be where a soil, when you look at the mineral material of the soil, it does not match the bedrock below it, meaning that the mineral material in the soil came from somewhere else, was transported there by a glacier or wind or a river or something, and is sitting on top of the local bedrock, but the local bedrock did not become the soil. Other mineral pieces did. Okay, once the material is broken down, weathered, what happens to it? We're trying to break down the mountains. What's that next step? What's going to happen? So we've broken the mountains, basically we're weathering them, we're breaking it all into little bits. That's just breaking into the little bits, which just make piles of little bits. There'd still be very large, tall piles there, but that's not what we see. They actually get weathered right down to flat. And in order for that next thing, which is going to be erosion, which instead of just breaking down the rocks, now we're actually transporting them to a new location. So weathering is the breakdown of rocks or breakdown of the Earth's surface. Erosion is taking those broken down bits and moving them to a new place. The agent, or what is doing the work of erosion, is running water, wind, glaciers, waves and ocean currents, gravity. So similar to what we saw with weathering, because it's really hard to separate these processes: weathering, erosion, and eventually deposition. If you look at all of these, they have something in common. Water runs downhill, wind goes from high to low pressure, glaciers flow downhill, waves are created by wind, and then gravity. They all have at their root, what is causing the motion there is the force of gravity. Okay, and one thing that we didn't list, but is human or biological activity. If a squirrel carries, or a birds eat rocks to help them digest their food. If they carry that somewhere, they die and decompose, or the rocks don't. They've moved that rock to a new location, or humans do a lot of this. So that can be an agent of erosion as well. There's a landslide or slumping would happen kind of catastrophically in an instant. This would be slow and over a long period of time. Glaciers, here we're actually looking at an ice fall where glaciers are going from a high valley down into a lower valley, and you see this kind of plunging into the next ice flow, and you see these large pulses of ice Each one of these black lines in here is where this ice is scraping the rocks away. This would be the abrasion by glacial forces. And then this is where two valley glaciers combine, and this is rocks. The rocks here, you can't tell the scale here, but some of these rocks could be the size of a car. Glaciers have a lot of force behind them because they are a solid that is moving like a liquid because it has all these little cracks in it. You can see all those cracks or fissures that are in there. Crevasses, sometimes they're called. Here's another image of a glacier. So we said that those black lines are where several glaciers from different valleys are all coming together. So you can see that this is many tributary glaciers. Glaciers coming in from the side are contributing their flow here. And this is a solid, it's ice, but you can see all these cracks allowing it to kind of bend around the corners. Glaciers are pretty cool. So this was taken from a aerial photograph, so from an airplane. Wind can have daily changes, just like the slow movement of dunes, or you could have more, again, catastrophic movements, something that happens instantly, like a sandstorm. Waves and ocean currents. So we talked about the ocean currents are moving. If they take sediments with them as they move around the globe, then that could be erosion, or the kind of constant pummeling and movement of waves at the beach. And if you've ever been in the ocean water at the beach, you know yourself, if you were a sediment, you know sometimes you go in at your towel, you play in the ocean, and then all of a sudden you end up 20 feet down the shore because the ocean wave currents are constantly moving things in what's called the longshore current. We'll be talking about that later. Running water. Here's showing a stream. This is not coming out of Willy Wonka's factory, and that is not chocolate milk. That stream is full of sediments. They are being carried up in the water column, not like the one we saw where they were bouncing along the bottom. This is that the particles are of the right size and shape, that they're actually staying in the water. We do see this white stuff here and here. We will talk about later this shape. You can see these kind of curves in here. We're going to talk about the shape and how it forms. And we'll talk a little bit more about streams later on. I'm going to leave you with a question to think about. On a worldwide basis, which agent of erosion do you think is responsible for moving the most material? So the glaciers were strong, the wind is kind of constant, we have the waves all around the coastlines, we have streams in our backyard, but then there's places on Earth that don't have a lot of streams, maybe in a more arid climate. So kind of think that through for a second. Get your idea of what you think, which one of those is causing the most erosion or moving the most material. And I'm going to give you here is U.S. rivers with tributaries. Remember, tributaries are small streams that contribute their water to a larger stream. So they're flowing into the larger stream. Here's that area I was talking about that is more arid out here. The southwest is more arid. There's fewer streams. But here where we live, we have lots of streams. Okay, streams are the answer. They are carrying the most sediment. Glaciers are very strong and powerful. They have a lot of force behind them, and they can carry very large sediments, but there aren't very many of them. Not right now. Maybe during an ice age that would be different. The ice ages would have extended, at times there would have been continental glaciers that extended all the way down to here. But right now, most of our material is being carried by streams just because there's so many of them. Okay, that's